Hi, my name is Christoph Willibald. I'm a PhD student at the German Aerospace Center. Welcome to my IROS 2020 presentation. I'd like to introduce you to our work on collaborative programming of conditional robot tasks that Thomas Eiband, Dongheui, and I developed at the German Aerospace Center. I'm going to present you our framework that allows non-experts to program robots simply by demonstration. Collaborative robots, as you see them here, gain more and more importance in the production over the last few years, since they allow safe human-robot collaboration and also provide an easy way to demonstrate motions or tasks by kinesthetic teaching. But in reality, what we see in the production today are often traditional robot programming methods that involve writing code manually and therefore require a great deal of expert knowledge and also consume a lot of time. That is why these traditional methods are not really suited to flexibly and intuitively program robots in the production. To solve this problem, we've developed a collaborative programming by demonstration framework that allows non-experts like shop floor workers to program conditional tasks simply by demonstration. These conditional tasks involve decisions on how to react to different observations. And this has conventionally been solved by, for example, programming if statements. But in our approach, during the execution of a robotic task, the robot automatically detects anomalies or new situations and then collaborates with the user in order to solve these new situations. And this will then update our task model or refine currently existing skills. I'd like to demonstrate our method with the help of a simple task example, where the goal is to manipulate an object from a start location to a goal location. And in case the object is rotated by 90 degrees in the start location, the robot has to reorient it and place it in the goal location. Our method starts with an initial user demonstration, where the user picks up the object in the start location and places it in the goal location with the robot. And this initial demonstration is then repeated by the robot in order to increase the variability of the demonstration. We record 15 different sensor values during the demonstration, which include the orientation and the position of the end effector, the forces and torques acting on that end effector, the gripper finger distance, and the grasp status, which indicates if an object is grasped at the moment or not. And we then use these different sensor values in order to learn multivariate Gaussian distributions in the form of a time parameterized Gaussian mixture model. And this Gaussian mixture model is then used as an input for a Gaussian mixture regression, which provides us with a vector of mean values and a covariance matrix for every time step. The probabilistic encoding of our skill is then used to generate a task model, a task graph in our case, which is in the beginning pretty simple and simply consists of the first initial skill. This initial skill is then used for monitored execution of our task. During the execution of that first skill, the robot detects an anomaly here because the object in the start location is rotated by 90 degrees and the robot senses an unexpected gripper finger distance and also an unexpected grasp status. You've seen that the robot is capable of detecting new situations during the execution. And for the online anomaly detection, we compute a Mahalanobis distance for every time step during the execution, which measures the difference between the commanded and the measured sensor values. And in case the measured sensor value for one modality exceeds an anomaly threshold for E consecutive time steps, then we detect an anomaly. An advantage of our method is that we don't need to manually specify this anomaly threshold, since we learn an independent anomaly threshold for every skill and for every modality of that skill based on that initial demonstration of that skill. So in case an anomaly was detected during the execution, the robot asks the user for help. The user can then decide how to proceed. He can either refine the current skill during which the anomaly was detected, which causes the robot to continue the current skill until its end while recording the sensor values. These sensor values are then used to again learn a new probabilistic encoding of that skill. Imagine if we want to program a task where the robot sorts different objects simply based on their geometry. Here you can see the expected force values for that sorting task. And in case the robot now picks up an object with a different weight, the robot will detect a force anomaly. But since the robot shouldn't decide based on the force of an object, the user decides to refine the current skill and incorporate the new sensor readings for the force into the probabilistic encoding of that skill. This will lead to an adjustment of the expected force values and also to an adjustment of the expected variances. That is how we can learn important features of a task while ignoring others. But in our case, the user wants to demonstrate a new skill and therefore decides to provide a new demonstration. This then triggers a teaching phase in which the user can demonstrate a new skill which will solve the new situation. Here you can see the user demonstrating a new skill, which the robot reorients the object and places it in the goal location. You've seen that the user demonstrated the new skill starting from the anomaly state. And this user demonstration is then again repeated by the robot in order to increase the variability of the demonstrations. And these two demonstrations are then again encoded in a probabilistic model of that skill. This new skill is then used to update our current model of our task. You can see the probabilistic encoding of the initial skill and of the newly demonstrated skill. We then split up the initial skill at the time step T alpha, which lies in between the time step where the sensor values exceeded the anomaly threshold for the first time and the anomaly time step. And then we insert a decision state here and also append the newly demonstrated skill to that decision state. During the execution, the robot can then decide based on the currently measured sensor values which skill to execute. As I've just explained, we can then switch to the monitored execution where the robot uses the updated model of the task. We evaluated our method with the help of an experiment. Here you can see our setup. We used a DLR lightweight robot and provided the user a graphical user interface with which he could interact. And we provided buttons to start and stop the user demonstration and to operate the gripper. We also informed the participants about the sensing capabilities of our robot and explicitly told them that we don't use vision. We evaluated our method with the help of 3 different state-of-the-art programming by demonstration methods, and we evaluated different knowledge representations and different teaching modes. Especially, we wanted to evaluate the influence of an artificial agent on the training data acquisition. In our case, the artificial agent actively requests for user input. In the first method, the user simply demonstrates different skills successively, which are then stored independently from each other in a solution pool. In our method that I've explained to you, During the execution, the robot automatically detects anomalies and then collaborates with the user in order to refine or extend our task graph. Where in the third method, during the execution, the user has to identify anomalies and then decide if and when he wants to demonstrate new skills. Here you can see the teaching of the initial skill, which is the same for all three methods. And now you can see a teaching of the second skill with the sequential batch method, where the user just demonstrates the second skill. And the second skill is then stored in a solution pool independently from the initial skill. And here for the teaching with our method, we assume that the user has already demonstrated the initial skill. And then during the execution of that skill, the robot detects an anomaly and collaborates with the user in order to solve this situation and to update our task graph. Whereas for the third method, the user has to observe the robot during the execution and decide when to demonstrate a new skill when he observed an anomaly. But as you've probably already seen, the user decided too early to demonstrate a new skill where the robot could not yet sense an anomaly. This is due to the discrepancy in the sensing capabilities of the robot and the user, because the user already sees the anomaly, but the robot can't detect it at that moment. This method also leads to a robot program which is unsuccessful during the execution because the robot decides too early here for the next skill at a time step where the robot can't sense a difference between these two skills and randomly selects one, which here is the wrong one and leads to an unsuccessful task execution. Whereas with our method, the robot decides for the subsequent skill in the correct time step, where the two skills can be differentiated, and this leads to a successful execution. The sequential batch method also leads to an unsuccessful robot program, because during the execution of the first skill, the robot now detects an anomaly and switches to a time step in the other solution of that solution pool, but skips the entire reorientation part and continues the second skill at a wrong time step, which leads then to an unsuccessful execution. We evaluated the performance of our method with the help of two tasks. The first task is the one that I've already explained to you and that you've seen in the videos. And the second task that the participants had to program consists of the same first skill, but in case an object is already located at the goal location, the robot has to bring the object from the start location to another goal location. We've asked two participants to program the two different tasks with the help of the three methods. And these participants didn't have any experience with the robot. And as you can see, only our method was successful in all four different tasks, whereas the sequential batch programming method was only successful in 75% of the executions, and the third method didn't succeed in any of the executions, which is due to the problems that I've just mentioned to you. And now to end my presentation, I'd like to quickly summarize our active learning framework that allows non-experts to program a robot by demonstration. The generated task graph guarantees a successful transition between skills in the decision state. And we've demonstrated that the involvement of an artificial agent during the training data acquisition has a positive effect on the execution performance. And we've also demonstrated that we can incrementally increase the complexity of the task without reducing the overall performance. Okay, now I'd be happy to talk with you about our work and to answer all your questions.